I hope it won't happen.
Let's start. So I will start recording now, Iris. Okay. Good morning, everybody. Welcome again for another seminar here at the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Iris Pereira Breda, and she will talk about the continuous rise of bulges out of galactic disks. About Iris, she initiated her academic studies in environmental engineering. However, she didn't feel fulfilled. So she decided to spend a couple of years outside the university, working to be able to financially support the studies. Then she moved to Porto and enrolled in the Master in Astronomy. There, her full dedication culminated in being awarded a PhD fellowship in the same university, where she had been deeply exploring secular evolving galaxies. In the following 1.5 years, she was hired as a postdoc fellow there within the same institution. And finally, in the last year, she moved to Granada after obtaining a Severo Ochoa postdoctoral grant to explore extreme emission line galaxies based on J-past data. So thank you very much, Iris, for accepting this invitation, for giving us this seminar, and the floor is yours.
Thank you so much. So as you saw, my internet, for some reason, it's very unstable now. Let's hope everything will be good, because I was already kicked out twice. Okay, so I'm here to talk to you about what I did in my master PhD in the following small postdoc fellow that I got in Porto. And basically, we were exploring secular evolution, as Rene said, mostly emphasis on bulges, but not only. So we studied, we studied deeply both the bulges and the disks, and also the bars of a representative sample of spiral galaxies. So basically, what I knew before starting my master and my PhD, it's that basically there is two types of bulges, which basically means that there is two types of spiral galaxies. So on the one hand, we have the spiral galaxies that host a classical bulge, and on the other hand, we have the ones that host a pseudo-bulge. The differences are striking. Only by looking at the images, one can understand that indeed there is a big difference between these two. So the classical bulges, basically, they are very red and big. And by looking at their spectra, we can understand that they are pressure-supported systems. And if we try to fit the surface brightness profile with the Sersic law, we will find a high Sersic index. Higher than 2, it's how we defined a classical bulge. Actually, basically, most of the times, people, what they do, it's simply this. So they fit the Sersic index to the surface brightness profile of these bulges. If it's higher than 2, we classify it as classical bulges, and if it's lower than 2, we classify it as pseudo-bulges. So yes, and on the other hand, the pseudo-bulges, they are much faint. They are usually blue, have blue colors. And if one goes and look at the stellar populations, we will see that they are rotationally supported. We also see that usually pseudo-bulges are mostly hosted by low mass galaxies, whereas classical bulges, usually they are hosted by high mass galaxies. So when they discovered the second type of bulges, these pseudo-bulges, that is recent, let's say, has some decades only, astronomers like myself, they understood that they come from very different, because they are so different, so they must come from very different assembly routes. So basically, how it's defined nowadays is that a galaxy hosts a classical bulge formed first its bulge through violent quasi-monolithic collapse, for instance, or mergers, and then it gathered its disk around it gradually. Whereas the pseudo-bulges, they are thought to be formed gradually out of the disk. So in one hand, we have the disk forming first for the pseudo-bulges that gradually gives rise of a central excess, which we call a pseudo-bulge. And on the other hand, we have the other spirals that are formed in a completely different way through first the bulge is formed and then the disk is accreted around it. So this means that we would expect a bimodal age distribution, and not only age, but in color and everything, because, I mean, if these two galactic structures, they come from two so different assembly routes, then we should be able to see it when we study them. So, but what happens is that the observational data that is available at most show high spread transition, never a bimodality as we expect from the theory. So the goal of this project was to clarify whether indeed the CBs and PBs, classical and pseudo-bulges, are really evolutionary distinct, or they are the opposite ends of a continuous evolutionary sequence. So let's start by thinking about what will be the limitations in previous studies. So I am lucky because when I entered in astronomy some years ago, maybe 7 to 6 years ago, IFU, integral field spectroscopy, was appearing. But before that, all the studies are based basically on single fiber spectroscopy or long slit spectroscopy. So we didn't have the power to spatially resolve the galaxy as we wished, like now we have. So this will introduce aperture biases, obviously, because, for instance, all the studies that are based on the single fiber spectroscopy, so the fiber has the size of the fiber, it's always the same, right? But so it depends if the galaxy is bigger or smaller, if it's further or closer. We will get different parts of the galaxy according to these things. So, for instance, in one case, the fiber will collect light only from one specific part of the bulge, a more central part, whereas for other galaxy, it can collect light from both bulge and disk, for instance. So, of course, this will introduce biases. Then we have, obviously, the spectral modeling biases, because, well, spectral modeling is not an easy task. It has many degeneracies. So we have to count on these two. And then regarding the structural analysis, so the photometric analysis, I told you before that basically we rely on the Sersic index to define whether a spiral galaxy is formed in one way or in another way, if it's classified as classical or pseudo. But actually the Sersic index, it's also subjected to one. There is a big degeneracy that is very difficult to solve between the effective radius and the Sersic eta. And obviously the adopted methodology that we use to model the bulge will also impact our results. So for this work, we tried to overcome these limitations. So for the aperture biases, we use IFU spectroscopy. For the spectral modeling biases, we repeat the analysis using two different stellar libraries and different stellar population synthesis codes. For the structural analysis regarding this degeneracy I told you about between the Sersic index and effective radius, I've developed a tool that is called IFIT, that fits the surface brightness profile of the bulge by fitting a Sersic index in a way that, in theory, it should be free from this degeneracy, at least in theory. Regarding the methodology to model the bulge, we try to be consistent and to minimize the use of methods that rely on strong prior assumptions that we might not be certain of. So we pass for the sample selection. So from all the CALIFA, we use the CALIFA survey in the study. So from all the CALIFA galaxies that we had, we took all the late type galaxies that are face-on or nearly face-on, that we clearly see the bulge, and we are sure that by taking spaxels of the bulge, we are not taking also disk, and non-interacting galaxies. We want pure secular evolving galaxies. So we end up with 135 galaxies covering all morphological types. Late type, obviously, morphological types. And we end up with a very representative sample of the local population spiral galaxies that covers approximately 3 decks in total stellar mass. So then we go to, the first step was to go to the surface photometry, because what we really wanted was to be able to isolate the bulge. So to know precisely what are the spaxels that belong to the bulge. So for this, we use the SDSS data. By using IFIT that I told you about, we decompose the galaxy into disk, bar, and bulge, as it's shown here, for instance, with the exponential disk in blue, then the bar is in purple, and the bulge after subtraction in red. We fit it, we get a Sersic index. However, we are not so interested in the Sersic index in this work. We are mostly interested, as I said, in the radial extent of the bulge, because this will determine the spaxels that belong to the bulge and the ones that belong to the disk and bar. And we also did something else, which is we decided not to subtract the disk and simply fit a Sersic profile to the excess luminosity in the center. And this is given by the orange line, so the bulge without subtraction. And this is what we took, this RB from the bulge without subtracting a disk. And for instance, in the image, we show you this circle that corresponds to precisely to this RB. So then we went to the computation of color maps and profiles with the SDSS data. And from this, we obtained all the color maps and color gradients also. And then from the images, in order to obtain radial profiles, we use a technique that is called ISAN, isophoto annually technique, which is supposed to be more reliable than the typical fitting ellipses, because it traces the morphology of the galaxy. So ISAN, what it does is basically to understand the isophotes of the galaxy, and then it takes it computes what is the area within this isophote, and to pass it through to a radial profile. Basically, it assumes a circle with the same area as it is inside this isophote. So like this, we are able to trace much better the morphology as compared to any other circular or elliptic tool that doesn't care about the morphology of the galaxy at all. So after having the radial profiles, as I show here, for instance, we also computed color gradients. So by fitting linear regressions to understand how the color is changing within the bulge and within the disk also. And then we went to the modeling of the IFS data. And by this time, FADA was not yet done. So Starlight, I suppose you are more familiarized with Starlight. It's a code developed to it's 100% stellar, so just takes into consideration the theoretical spectra of stellar populations, and with a combination of these SSPs, as well as simple stellar populations, it tries to fit the observed spectra. FADO, it's another of these codes, but that takes the nebular continuum into consideration, the nebular contribution into consideration. But by this time, we didn't have it yet, so this study is basically based on starlight. So we take the CALIFA V500 data, and we put it on Porto 3D, which is our pipeline in Porto to do spectral modeling in a spatial resolved manner, and it's based on starlight, as I said before. So for this, we use two different libraries, spectral libraries. The first one, it goes up to only the solar metallicity, so it has 4 different solar metallicities, with a maximum being 1. 4 metallicities with a maximum being 1 solar. And then Z5 that includes all the Z4 SSPs plus 1.5 solar metallicity. So in the end, it comprises approximately 38 ages between 1 million year and 13 gigayears. And we put it to run for several months, all these 135 galaxies, spaxel by spaxel, with these two spectral libraries. After some months, we have the results, and we start to compute the maps of all the quantities of interest that we want. For instance, the stellar mass, present and the one that was ever formed through the life of the galaxy, mass and light weight, stellar age and metallicity, stellar surface density, several emission lines that we wanted to study, etc. And as we did with the colors that I was saying before, in the maps of the colors, we also applied the Islam technique in all these maps in order to obtain radial profiles of all these quantities that we are interested at. We also classified the bulges according to their activity, let's say, by BPT diagnostics, using 3 different methods. But in the end, they were consistent between each other. So, okay. And after that, we post-process the results from starlight with remove young. So remove young is another tool from Porto that was developed in Porto that allows to spectroscopically subtract the contribution of stellar populations that are older than whatever we want. So we define an age. So basically, it analyzes the best fitting stellar population vector, so the output from starlight in this case, that can be FADO or PPXF or any other of these tools, and it computes the synthetic spectrum images and magnitudes in different filters by convolving with the filter transmission curve and stellar mass maps of the stellar old component. We adopted 8 different TCATs, we call it TCATs. So the ages that we will remove all the young part of the contribution. So we used 30, 100, 300 million, and 1, 3, 5, 7, and 9 gigayears. So basically, for instance, if we are talking about the TCAT for 9 gigayears, basically what we will observe will be the light that comes from the galaxy after being stripped of all the stellar populations that are younger than 9 gigayears. And then we did the same for the 7, for the 5, and so on, so that we can see basically how assuming that there's no radial migration, obviously, we can see how the stellar mass builds up in the galaxy. For instance, this is a GIF I did with Muse, it's not the CALIFA, much better resolution, and remove young. So you see basically the galaxy is being stripped by its younger stellar populations, so that for instance, the last image you see, the most faint image, is the one that has only the light contribution of 9 gigayear stellar populations. So this gave us, after again taking these images, processing it with design, we obtained radial profiles. And here we have 3 exemplary cases for our sample of the CALIFA galaxies, as I was saying. So if one looks at the radial profiles, it's very interesting to see that there are striking differences between these galaxies. For instance, if we look at what we call the interval A galaxies, so the first one, we see that there is a nearly homologous stellar mass growth through all the galaxy, because independently if it's in the center or in the disk, we see that more or less this, the different radial profiles that you see in different colors correspond to these different stellar populations with different ages. So for instance, the red will be the correspondent for the stars that are only older than 9 gigayears, and so on. For instance, it's 9, 7, as I said, 5, 3. For instance, the green corresponds to all the star populations that are older than 1 gigayear, and so on. So indeed, what we see is that basically the disk shows always a quasi-homologous growth in every galaxy, but not the bulge. The bulge tells us a very different story depending on the galaxy. So for the IA galaxies, the first ones, the top ones, we see that indeed their bulge and the disk, they are more or less the same. They grow more or less the same pace. But if we look at the IC galaxies, the bulge has no star formation since like 9 gigayears, because all of the light that is coming from there, it's equivalent basically to the contribution of 9 gigayears light. And then we have the intermediate kind of galaxies that are, let's say, between these two. It's not that their bulge was formed 9 gigayears ago, but it's not like it's forming at the same pace of the disk like IA galaxies. So by this, we devised a parameter, let's say, which we called delta mu 9 giga. I will call it only delta mu, which is basically the difference between the total light and the light contribution of stellar populations older than 9 gigayears, this only within the bulge radius. So basically, for instance, for the interval A, we can see from the plot that it can be about 2 mag, 1.5 to 2 mag, whereas for the interval C galaxies is nearly 0, this delta mu value. So this is an extinction and distance independent indicator of the bulge evolutionary status, and we use this to classify our sample into these different intervals, A, B, or C. And this is the result. So, or one of the results, the most important results, let's say, from this work. So the first panel, panel A, serves only for us, for you to understand how I devised our galaxies into class A, B, and C. So it shows the mass stellar age versus delta mu, and well, you can see the ones that I classified as blue are that I painted blue. Sorry, are classified as IA, then the green, and then the red. So this is a bit arbitrary, but it's only to be able for us to follow if in the other the subsequent correlations that we might find, if this still holds, and indeed it does. You can see that there's all this class C, for instance, they are always in the right side most of the plots. The B are in between, and the IA are down. So then the panel B shows the mass of the bulge versus the mass weighted stellar age. And as we can see, there is a clear continuity and correlation between these two parameters. Then I show you the total galaxy mass versus the mass of the bulge. Again, a very clear correlation. Then the mass of the bulge versus the mass weighted stellar age. the mass of the bulge versus the bulge stellar surface density, and the BPT diagrams. So what do we see? We see that basically there is a continuity, point number one. This is striking. There's no bimodality as we would be expecting if these two would come from two different, completely different assembly routes as we learned from the state of the art. Besides that, we see that our class A bulges, they are always low mass. They are hosted by low mass galaxies. They are younger. They have lower metallicities in their stellar populations, and they are less dense. They have lower stellar surface density. And also, if we look at the BPT, we will see that they are star formed. They are classified as star forming. And if we go to the other side of the spectrum, let's say to the IC galaxies, these are the more massive bulges, older, hosted by more massive galaxies. They are more metal enriched, and they are much more dense. And by looking at the BPT, usually they are classified as linear or cipher or composite. And then we have the IB right in between. Another interesting thing I would like to tell you is, if you notice, there is a gray star that represents the values that we know for the Milky Way. And when I put the values that we know, it follows beautifully all of these trends, which is very interesting. So we continue our analysis to compare bulge and disk. And it's very interesting to see that these two are correlated. They are even for the IC, that supposedly they are formed independently. They are quite well correlated between each other, independently of the SSP library that we use. So on the top, it's for the Z4, the ones that the library that goes only until 1 solar metallicity, and the down one, it's for the 1.5. It goes up to 1.5 solar metallicity. The results are consistent, and as I said, there is a clear correlation between these two stellar components. However, it's interesting to see that in the low mass part, so our class A galaxies, basically, their bulge and disk is indistinguishable, basically. We see that there is no big differences between I'm sorry, I was saying it was different spectral libraries, but no, it's for the stellar age and the stellar metallicity, sorry. So both the stellar age and metallicity, they are basically the same for the IA galaxies, and they diverge more and more and more, but still they are correlated even for the high mass galaxies, the IC. Then we go for the stellar age gradients. So we computed what would be the difference between the age in the center and in the periphery of the bulge for both mass-weighted stellar age and luminosity-weighted stellar age. So, and here I show for the two libraries. So Starlight Z4 in the left-hand side and the Z5 in the right-hand side. So the Z5, just to remember, it's the 1.5, goes to 1.5 solar metallicity. And again, the results are consistent. There is again a continuity, not a bimodality. And what we see is that basically the class A galaxies, they have positive gradients, which means that they are forming stars now mostly in the center. So the center is younger than the periphery of the bulge. Whereas for the IC galaxies, it's the opposite. So we see that the periphery is older than the center. It's younger than the center. So basically we interpret these results in a way that basically because the potential, well, it's right in the center of the galaxy, the gas will condensate faster there. So now that we're in IC galaxies, that now in the present day they have so much available gas, which is not the case for IC, the gas condensates in the center, so this is where there is more star formation as compared to the periphery. However, there is also in the periphery. But that's why then in the center we have younger stellar populations as compared to the periphery of the bulge. But then if we imagine that this bulge grows, right, it's forming stars, so it's growing until a certain point where something happens. For instance, AGN feedback happens. So that there will be a quenching, inside-out quenching episode. So if one thinks that the quenching will start from the center, will travel, let's say, to the periphery, and this will take some time. So basically, the center will be quenched first, whereas in the periphery, the star formation will still continue. And that is why we see the opposite effect. So negative gradients, age gradients for these icy bulges that are already quenched. We saw since 9 gigayears at least. And recently, I'm back to this project. I decided to explore better. So because these are all average quantities, it's the mean age, the mean metallicity, and so on. So now we've decided to go again to be sure that, because what happens with mean quantities is that they might not represent a continuity, let's say, because imagine if one has two star forming episodes of equivalent intensity, one now and another 10 gigayears ago, we will have a mean age of 5 gigayears. So this is not representative of what's really happening in the galaxy. So now I'm exploring the individual star formation histories of these bulges, just to be sure that our mean quantities that we derived are representative of what is really happening. Yes, indeed we see. So for instance, in the left-hand side where I show the star formation histories, the right-hand side is the star formation rates for the different galaxies. On top, from the top is IA and IB and then IC. And basically this is all the galaxies overplotted, let's say, for these three different classes. And we see indeed that the star formation histories of IA galaxies are much more slow as compared to the IC. The IC was faster and earlier, whereas the IA, it's going much more slowly in a more continuous way. And the star formation rates show more or less the same phenomenon, the same thing. So with these plots, we derived these two things. So in the left-hand side, I show you the T80. T80 is the time necessary for these bulges to acquire 80% of its mass. And again, here I show you also the disk. So the disk is with the small circles and the bulge, the big circles. So indeed we see that for these low mass galaxies, they took much longer time to acquire 80%, to assemble 80% of their mass, as compared to IC bulges that they did this very fast and very early in time. And in the right-hand side, I show you the e-folding time. So by fitting declining exponential star formation history, let's say, we obtain the folding time, and again, this is what we see. It's recurrent, this shape, this continuity, and this shape where IA galaxies, their bulges and disks are basically the same, and the higher the mass, the higher it's the difference between bulge and disk, but still they are still very much correlated between each other. So let's go back to the question, is there an evolutionary sequence in late type galaxies? So as I showed you, and as I said over and over again, our results are indeed incompatible with the bimodal age distribution in the bulges of spiral galaxies, which is implied by these two distinct assembly routes I explained you, one directing to old monolithically formed CBs that form independently of their disks, and other that emerge through quasi-continuous star formation in the center of secularly evolving disks. Instead, our analysis suggests that bulges in disks evolve alongside, which leads to a continuum of physical and evolutionary properties, as is exemplified by our intervals, by our delta mu intervals. Additionally, according to our results, we see that all late-type galaxies, independently, they appear to follow the same evolutionary path. However, having different evolutionary paces or metabolisms, as I like to call, which is dictated by the total galaxy mass. So we are already familiar with this by the downsizing scenario when we talk about galaxies on their whole, so that more massive galaxies, they evolve faster as compared to less massive. And here what we see, it's a kind of a subgalactic downsizing scenario for the bulge. So basically, they follow the same evolutionary route, let's say, but the ones that are more massive, they evolve faster. And here it's a scheme that we present on the first paper regarding this analysis, where we try to explain this. So we don't know if IA galaxies form a bit later or at the same time of IC. We leave this space. There's no way to know for sure. But what we propose is that if you look, so basically that rotating disks will be the first structures to be formed. So if we have a huge mass of gas that is rotating because everything in the universe dances for some reason, so it will get like a pancake, right? And it will form a disk, basically. And then what we suggest is that the gravitational potential well, which is much higher in an icy galaxy, so in a cloud that starts as being very massive, will promote inside so the gas will travel very fast inside for icy galaxies, which have a very deep potential well. So it's very easy, and since also the gas is dissipative, it's very easy for the gas to travel to the center. So this means that for these massive galaxies with deep potential wells, very early in time and very fast, the bulge will form because huge amounts of gas will travel to the center where they will collapse to form the bulge. But for IA galaxies, this will happen the same, but in a pace that it's much slower. That's why even today, and maybe probably not even 30 gigayears, IA will be IC because the pace is much slower. But okay, we propose that it's exactly the same assembly route, let's say. And then at some point, what you see is that in IC galaxies and also some in some IB, at some point the AGN will turn on, that will quench the bulge and it will stop its formation. And then, okay, we continued because another question I had was regarding the disk of the disk inside the bulge, because what is assumed when one goes to do surface photometry, the first thing we do is to model the disk outside the bulge in the bar. We model it with an exponential. We assume that it goes exponentially growing until the center. We subtract it, and then we fit to the remaining light, we fit a bulge in a bar if that is the case. But for me, it was always, I always had the question if indeed there is an exponential disk inside the bulge. First, because by considering class C, for instance, the more massive galaxies. So what we learn from the state of the art is that the bulge will be formed first and then the disk will be accreted around it. So it's strange that by having already a very kinematically hot stellar component such as the bulge, it's strange to me how the disk will be formed later on and will still be able to to be formed with an exponentially, so that its maximum, it's inside the bulge, after we already have the bulge formed. And also, even if they form at the same time, I was always wondering that because these bulges, for instance, they are very hot kinematically. So I was always thinking that the interaction between bulge and disk should somehow hit the cold orbits of the disk. And this with time might mean that the disk won't be disk anymore, it will be transformed, let's say, in a bulge. So we thought about an experiment on how to test this. And what we did was, so we went to the photometry and we fitted a disk with 3 different configurations, as it's shown here in this image. The pure exponential in the blue, a flat disk that after the radius of the bulge inside the radius starts flattening, and a decreasing. So after the RB, when it enters RB, it goes until 0, basically. And this is the photometry. And then we went to the spectroscopy. And so this is a kind of a hybrid approach. So we computed the integrated observed spectrum of the bulge. So we summed all the spaxels that belong to the bulge. And we went to the disk and we took, we computed an average representative spectra of the disk. We modeled these 2 spectra with starlight and fathom. And we determined the best fitting stellar spectra. Then we compute the scaling factors for the observed disk by integrating the observed SPPs. So basically, by assuming these 3 disk configurations, as I told you, we asked the question, what would be the fraction of light that corresponds inside the bulge area, inside RB, what would be the fraction of light that corresponds to the disk if we assume it to be exponential, flattening, or centrally depressed? And with this information, we went back to the spectroscopy, and basically we scaled the spectra of the disk in a way to be compatible with what we were seeing or what we were measuring in the photometry. So we scaled it accordingly. For a pure exponential, this will be what we have to scale, for the inwardly flattening, for the centrally depressed. And then we subtract, and we look on our residuals. By refitting them again with starlight and fathom. So basically what we saw is that by doing this exercise, independently of the total mass of the galaxy, approximately 1/3 of our sets obtained after subtracting an exponential or inwardly flattening model yield negative flux, mostly in the blue spectral range. So basically after scaling our typical spectra of the disk and subtracting to our total, assuming an exponential, the exponential law, we obtain negative flux. So something we are doing wrong, right? Apart from that, approximately 1/3 again of the disk subtracted bulges reach the maximum age or metallicity of the library. This is also an indication that something is wrong. And approximately 1/3 of the stellar mass after subtraction is higher than the one that we originally had. Again, something is wrong here. So this study suggests that a significant fraction of late-type galaxies, the disk cannot show, at least with our assumptions, it cannot show neither exponential or inwardly flattening. It must have a central depression inside the bulge radius. So I will go now for the conclusions. Our combined analysis of very representative sample of the local spiral galaxy population by using surface photometry, special results of spectral modeling, and revealed that our bulges span a continuous sequence of increasing delta mu with increasing mass, stellar surface density, age, and metallicity. There is clearly a lack of an age bimodality, which argues against the two distinct bulge assembly routes and suggests instead a unified scenario for the formation of late-type galaxies. We also see that the total stellar mass of the spirals is what regulates basically the assembly time scale of the bulge, and also of the disk, but of the bulge in a more intense, let's say. So we call it like the galactic metabolism, so that in low mass galaxies, this metabolism is very slow, but for high mass galaxies, it has a higher metabolism. We can also see that bulges undergo an interwoven evolution with their parent disks. They do not appear to evolve separately, to the contrary. And finally, we see that for a substantial fraction of local spiral galaxies, the parent disks cannot preserve its exponential intensity slope inside the bulge radius. Thank you so much for your attention.
Thank you very much, Iris, for this wonderful talk. And now the talk is open for questions. Please raise your hand, and then you're allowed to make the question. Okay, we have a question by Rosa. Go on, Rosa, please.
Hello, Iris. Thanks for the talk. I have a comment and a question related with the methodology that you have followed to subtract the bulge component. What I understand is that you take the images, HST images, and you there fit the profile, and with this the solution of this profile, you retrieve from the data queue from CALIFA the bulge and the disk component of the galaxy. So I wonder how they must be affected by the change of the observing condition to make this extrapolation. Also because there is well, I don't know if you have the possibility to compare this result with the result that Jairo Mende obtaining doing a similar analysis, but using only the CALIFA data. So they use a code that he did, where they, in a very consistent way, they use all the data queue at all the wavelength to retrieve the bulge and the disk component. So do you like to comment this?
I'm not familiar with this work, so on this I cannot comment. But just say we didn't use HST imaging data, we used SDSS data.
So, yeah, okay.
Well, just a detail.
It's independent of the CALIFA data. Okay.
Yes, independently of the CALIFA data. Yes, I mean it should be consistent, right? We expect it to be the same, whether if it's observed in SDSS or it's just because with the CALIFA usually it goes it doesn't observe the whole radial extent of the galaxy. So if one wants to fit properly a disk, it's not that maybe with the CALIFA one can also do that, but because the SDSS it goes further away because it has higher sensitivity, so we see more of the disk that we can, in theory, maybe model it better, but it should be the same.
But something that I don't have clear, you have taken into account is that the modeling of the radial profile must depend of the wavelength. So that's why it is good to do this analysis for using the data cube instead of external images, because
sure,
must
sure.
depend on the wavelength and how do you translate this wavelength dependence to extract the spectra from
we corrected from this. So we took in consideration the transmission curve of the filter, and we corrected for this effect. So we saw that, okay, within, let's say, the R filter, the disk, if we assume a pure exponential, should be, I don't know, 30% of the total that we see in the bulge. And then in order to scale the observed spectrum as extracted from the CALIFA, we took this into consideration. We corrected from this effect so that we are sure that we are consistent.
Okay, I think
but this is
complicated than this, but I
Sorry?
think it is more complicated than this, but anyway.
This is all
nice
published. You can, if you want, I can send you
several papers in this line related with the code and also the result. In general, result, it was not only for the for a sample of later galaxy. It is for different type of galaxy. Okay. And the other question is related with did you take into account if the galaxy has a bar or not for the modeling or internal bar?
For this particular project, no. We did it independently of if it's barred or not barred.
Okay. Okay, thank you.
No problem. Thank you.
Okay, thank you, Rosa. Another question for Iris? Okay, seeing none, let's thanks again, Iris, for this talk. And great talk, say Pepe Vilches in the chat. And thank you again for your talk, and see you all participants in the next seminar.
Thanks so much for the opportunity.
Thank you. Bye.
Bye.